He's joining us remotely. And Professor Rajaratnam will speak on advances in modern large-scale statistical inference with applications to graphical data.
So I hope you can hear me. If not, please let me know and I can speak up louder. First, a word of thanks to the organizers and the Field Institute for the invitation to speak at this conference. And I apologize, I cannot be there in person. I was hoping to be there in person, but due to extenuating circumstances in terms of family health has prevented me from being there. So I apologize for that. But first, I also want to acknowledge Professor Gérard Letac, and in celebration of his 80th birthday. First, I hope to give a scientific talk, and thereafter I hope to say a few words about Professor Hélène Massam in commemoration of her. So without any further ado, I will start. So the title of the talk is Advances in Modern Large-Scale Statistical Inference with Applications to Graphical Models. And this is going to work with Professor Alfred Hero from the University of Michigan, Ann Arbor. I'll first motivate the talk. So modeling multivariate dependencies is something that we are all faced with, often on a daily basis, at least in statistics. So, and that is often has been due to the availability of high throughput data from various applications. So there has been a compelling need for methodology and tools for analyzing high dimensional data. And we hear this word high dimensional everywhere. And with high dimensional modern data, there is certainly a need for methodology and tools. Of course, examples are widespread, in biology, gene expression data, single nucleotide polymorphism data, and more modern data. And in the environmental sciences, where climate data on very fine spatial grids, lots of features and perhaps sometimes limited samples. In the field of finance, returns on thousands of financial instruments, and in retail, consumer behavior. So these are just some of a few of many examples where we are in a position to collect really large amounts of data, modern massive data sets. But there are some common goals, right, when one tackles even these quite varied data. And one of them is to understand complex relationships and multivariate dependencies that are in the data, and to formulate correct models and perhaps develop inferential procedures to understand data and test hypotheses. So this is the main motivation for what I hope to discuss today. And of course, one of the poster childs of undertaking analysis of modern high dimensional data is the Lasso, and it doesn't read any introduction. And we know classical regression, as we have it on the slide. Our goal is to minimize this empirical error, and of course, the modern version of it, one of the modern version of it, right, in terms of model selection or variable selection, is through an L1 penalized or regularized likelihood. Now, this is, of course, has been a popular approach for the last, I would say, as many as 25 years now, so a quarter of a century, perhaps. So the advantage, of course, is that one obtains a solution that's sparse. The method achieves model selection, and adding an L1 penalty term, right, introduces sparsity. And the penalty parameter, of course, lambda, controls the level of sparsity. Since the solution is not available in closed form, unlike the classical regression OLS estimator, there has been a recourse to using convex optimization to solve this problem. And in fact, the L1 penalty that we see here is seen as a convex relaxation L0 or model selection penalty. So we've seen this being tackled in the area of compressive sensing, sparse signal recovery, the last so, and there are a whole host of researchers who have contributed to this. And I'm just only mentioning a few, but there are so many more. So this is one of the poster childs of modern statistical method. I would not, however, call it statistical inference for the following reasons. It certainly has many strengths, right? It yields sparse solutions, so therefore, we can really try and understand what's going on better. It leverages convex optimization theory, and there are signal recovery guarantees as both the sample size and the dimension go to infinity. So it does. There is much theoretical safeguards that has been written about and produced in the literature. So that gives it a lot of I would say theoretical underpinnings. And we've seen that this entire body of work has had contributions to and from and connections with other branches of mathematics, including optimization theory, harmonic analysis, functional analysis, and so forth. So there are several strengths to this body of work, but there are certainly challenges. One of them is that when one does use convex optimization, often employs iterative techniques. So these methods are not scalable to today's ultra-high dimensional settings. When you have 1,000 features or 10,000 features, yes, perhaps. But when you have 1 million or 10 million variables or features, optimization or iterative methods, where one needs to employ iterative methods, can often be not scalable. So they don't really speak always to modern ultra-high dimensional settings. But what I think is perhaps a bit more serious is that these methods are not immediately amenable to statistical inference. One puts an L1 penalty, one produces a model, and one's not clear how stable that model is. We're not testing a hypothesis. We don't have the underpinnings of statistical inference because it has been difficult to quantify the probability distribution of these estimates. There has been some progress, but it's been limited. And emphasis has been on model selection or variable selection and less so on inference. So uncertainty quantification, of course, right, has now taken a top priority in inference, especially in ultra-high dimensional settings, because of the lack of uncertainty quantification or inference in this modern settings. And certainly the reason is obvious. It is very difficult to quantify the probability distributions of estimates in very high dimensions. So an understanding of central limit theorem type results in ultra high dimensions. So the reasons I would say are obvious, whereas it is easier perhaps to put an L1 penalty. And another challenge is the need to select a tuning parameter, a penalty parameter. So that is, parameter has to be chosen. That's often chosen either by cross-validation or through some information criteria, and that can lead to unstable models. And so with that said, the consistency that we get of these methods, right, are not really applicable in the setting when the sample size is small. They require both the sample size and the dimension, both of them, to go infinity, as I have here, right? But when n is small and fixed, is what we often get in many biomedical settings, or what we call sample-starved settings. For example, in biomedical settings, when one studies cancer, often you have 60 individuals in a control group and perhaps 70 in an experimental group. N is hardly going to infinity. So that is, the asymptotic regimes in So is theoretical guarantees for the latter has been proven, doesn't directly always speak to the modern sample start settings. And a lot of the assumptions in proving this assume some kind of sub-Gaussianity of the data. So these are some of the challenges faced by these methods. That doesn't mean to say that these methods are not useful. They are, of course, very useful, but there are certainly some challenges, especially the lack of an inferential basis, probabilistic quantification, the mathematical rigor behind understanding these, these high-dimensional quantities. So the lasso, of course, in the regression setting has been a poster child. So I'll then move on to another area which has also benefited from recent advances in L1 regularized estimation, is the area of understanding correlations and modeling relationships. Now, I don't think I need to tell the audience here what a correlation is, but I'll go through it for the benefit of students. So we know the correlation as a basic measure of linear pairwise relationships. And the covariance matrix sigma collects these relationships together. And an estimate of sigma is often required in procedures such as principal component analysis, canonical correlations, and MANOVA, etc. Now, so estimating sigma or its inverse is certainly of statistical interest. But it is estimating, it's very challenging in high dimensions, right? And the manuscript by Puramadi, for example, outlines this quite well, in addition to several papers. That said, well, of course, the reasons for that is quite obvious. When we have a P by P covariance or inverse covariance matrix, it has of order P squared elements. And estimating order P squared parameters with classical estimators is often not viable, especially when the sample size is much lower than the dimension. So in our modern sample start setting, when the dimension is much larger than the sample size. So often the approach that we have seen is to try and reliably estimate a small number of parameters in sigma or omega. And we call this, model selection, where there is an attempt at zero or non-zero structural recovery. And this gives rise to sparse estimates of sigma omega. And in the covariance or inverse covariance context, we can represent the sparsity by graphs and networks. And sparse estimates are viewed as approximations to underlying sparse models. So in this sense, what we've seen is also L1 theory has been brought to bear in this area. So I just wanted to quickly reflect on these two models as motivation before introducing the methodology in this talk. So for example, let's assume y1 up to yp has a normal distribution, right? It's a p-dimensional vector with mean 0 and covariance sigma. We denote v by the index set 1 up to v. We know very well in the Gaussian setting that the covariance matrix sigma encodes marginal dependencies. So if yi is independent of yj, the covariance between yi and yj, right, is 0. So the ijth element is 0. Now what's perhaps more interesting is the inverse covariance matrix, and that encodes conditional dependency. So if yr is independent of yj given the remaining variable, there is a 0 in the ijth element of omega. And these classes of models are known as Markov random fields. We've seen the work of many authors and some in the audience who have contributed so significantly to this area, including Pearl, Stefan, David Anani, and Joël Letac, and Alain Massam, and others, and many others. So this is an area which has also benefited, right, from modern inferential techniques. So the graph, you can use a graph to summarize the relationship between the nodes. And for example, if the ijth element in omega is 0, we drop the edge between I and j. And here is a simple example where we build a graph from a sparse omega. So between b and c, there's a 0, so we drop the edge here. And many of you in the audience are familiar with these classes of models. So how have researchers in the last 20 years tried to build these models for modern data? Well, of course, one of the obvious approaches is to put an L1 penalty on the parameter of interest to induce sparsity. So one popular approach is to take the Gaussian log likelihood and to put an L1 penalty, right? Where S represents the sample covariance matrix. And this problem is often referred to as the graphical lasso, and it can be solved, right? It is an optimization problem and can be solved by using optimization techniques. And adding this L1 regularization term introduces sparsity in the inverse covariance matrix. So we will get zeros, right? Often this is a high dimensional inverse covariance parameter, and the penalty parameter lambda controls the level of sparsity, of course, similar to the regression setting, right? It is a parametric model that we are looking at, so it is sensitive to outliers, but there are advantages because we have a log concave function, so we can leverage convex optimization theory to solve this, right? That it's often was considered a scalable problem because you can apply convex optimization problem to problems of dimension, let's say 1,000, 10,000, and so forth. So it's considered scalable, but going beyond that, because of the iterative nature of these optimization methods can be onerous. And there are asymptotic guarantees, just like in the lasso setting, as n and p go to infinity. There's been many contributions since the work of Banerjee et al. Here, methods called Quick and G-ISTA and G-AMA. So we've looked at these where we've tried to scale these methods up so that they can be solved in real time for modern data. But there are issues. Of course, there are some these one-based methods in this covariance estimation approach that first, it yields sparse solution, and that's what we want. It does model selection, and it leverages convex optimization theory. Again, we have signal recovery guarantees as both the sample size and the dimension go to infinity. So it does try to address the modern regime from a theoretical perspective. And just like the lasso, it has contributions and connections with other branches of mathematics, including harmonic analysis and convex optimization and so forth. So I don't mean to say it doesn't have many advantages. On the contrary, I believe it does. But again, right, by just doing model selection, it does not have an inferential basis. So that is a big challenge. And again, just like the lasso, these methods tend to be iterative, so they are not scalable to the very modern high-dimensional setting. So all the issues with the lasso or L1 penalized methods are here also. The need to select a tuning parameter and the consistency or lack thereof in the high-dimensional setting when n is small. Often we don't have data which the sample size which runs up to infinity. So it's not so clear whether these theoretical safeguards are relevant or applicable in some of the modern sample start regimes that we find ourselves in, and also some of the assumptions that are used to prove results in this area. Of course, the role of convexity in inducing sparsity comes via optimization. So my hope was to use this to set the tone or the picture for what follows. So how do we overcome this, perhaps? And this is where I've summarized the various asymptotic regimes that we've seen in the literature. The classical one, where which I call small dimensional, where n goes to infinity and p is fixed, and I call that small data, in the sense that classical data, where we've proved, where the statistics community and the information theory and the mathematics community has proved results in terms of theoretical safeguards. And in the last 20 years, maybe we've had mixed asymptotics where both n and p go into infinity. And often these are referred to as high dimensional settings or very high dimensional settings or ultra high dimensional settings. That's what we've seen certainly with the lasso. But the more ultra modern setting where the sample size is fixed, but the dimension goes to infinity, has received less attention, what we call big data, at exascales. And so, which I call purely high dimensional, this has received less attention where n is fixed, right? And p goes to infinity. Can we recover, right, a graphical model or correlations in these regimes in a rigorous manner, in a principled manner? Those are the questions that we ask. And what we propose today is an approach which tries to, make some progress in this. And it's motivated by the lack of scalability of L1 penalized procedures. So here we propose a novel probabilistic mathematical approach which to overcome this and gives the inference or uncertainty quantification that is lacking, in many lasso-based methods. So, and we believe that this approach can lead to the discovery of large significant, so statistically significant parameters with mathematical guarantees. Now, in order to motivate this and give intuition, so consider a null model where you have a covariance matrix or correlation matrix, which is the identity, i.e. there are no true correlations. They're all zero correlations. So there are no discoveries, there are no signals. So any edge that we detect in a covariance graph, for example, let's say you build a graph based on the correlations, anything that is detected as non-zero will be a false edge, or what we call a spurious discovery, right? So I just want to show you how the correlation behaves as the dimension gets larger. Example where I fix the dimension p equals 100, and I look at generate correlations from a null model, which I call sigma equals I, and look at all the correlations. Now, okay, which I get from the sample correlation matrix, which is 100 by 100 matrix, but my sample size is 100, right? Now you can see that they're certainly distributed around zero because that is the true parameter, although there are no correlations, and you have some fluctuations around zero, but they're very far from 1 and minus 1. So you can clearly see that these correlations are small. Now let me decrease the sample size from 101 to n equals 25 and work out the correlation, the distribution of the correlations. Now the largest one here is 0.63 as compared to the largest one in the previous setup was 0.34. So you can see when the sample size is low and the dimension is to the sample size, we can get a correlation as large as 0.63, a spurious one. So in order to really kind of distinguish a true correlation from a false one, I do need to cut it off at 0.63 or find an appropriate threshold which takes away this noise, because we know that any of these correlations which are non-zero are really false correlations. Now let me go to the setting when n equals 10 and p equals 100. So I'm going to decrease the sample size even, right? Yes, and make it even lower. And the largest correlation here is now almost at 0.9. So it's at around 0.89. So you can see we can get a really large correlation. And some domain scientists would get really excited thinking that this is a really true discovery, when in fact, right, it's in fact an unfortunate artifact of the high dimensional nature of the problem that we have. Right? So as your sample size is much lower than the dimension, we get this phenomena where we get lots of false discoveries. So especially when the sample size is low relative to the dimension. So the probability of obtaining false edges are higher in the graph, right? So what we've tried to do is to try and see how to obtain, right, in a mathematically rigorous way, phase transition to control, right, the probability of obtaining at least one false edge. And there's been work that's done by my co-author and one of our students. It's a more recent work in this area, which I will briefly talk about today. So a question that you could ask is, well, where should I put this threshold to really remove, to kind of really threshold these false correlations? Because in these setups, right, how does one think about it? We want to understand where the threshold should be. Now, when the sample size goes to infinity and P is fixed, what happens is that we know that this distribution will become tighter and tighter around zero, in the sense that we'll get a sample, we don't need a very large threshold, right? So the probability of exceeding a certain threshold will go to zero, because this becomes tighter and tighter around zero. On the other hand, when n is fixed and P goes to infinity, as you see here, but even if I put a threshold somewhere here, let's say at 0.95, eventually when P goes to infinity, the largest one will breach that threshold. So we really can't put a threshold at some fixed value, 0.95, because it will still yield, right? That such a procedure will still yield a false or spurious correlation. What do we do in this setting? So one way to think about it is, well, a higher threshold, certainly, rho, to detect or to separate signal from noise is required to avoid detecting false edges. Now, and that should really be a function of P. So let's consider the probabilistic quantity. What's the probability of obtaining at least one false edge? I call it PE under the null model. So it's a very simple setup. So sigma is equal to I. So you have a P by P sigma. And I'm going to generate samples from S. And I want to see, right, what's the probability of obtaining a false edge when I use rho P as the threshold at which separates signal from noise, a true correlation from a false one. We know, as I said, for fixed n, right, and fixed rho, like here, if I fix the sample size and fix the correlation threshold, right, and if the dimension goes to infinity, the probability of getting a false edge goes to 1. It rushes to 1, because we will get a false edge which will breach the threshold, right? Which will breach any threshold if you fix the sample size and the dimension goes to infinity. So one way to overcome this is to let the threshold rho tend to 1 so that the probability PE is small. So we can let perhaps the threshold also tend to 1. Now, if you're a fixed sample size and a fixed dimension P, right? If the threshold goes to 1, then of course, the probability of detecting a false edge goes to 0. Now, if you move the threshold, right, and move it to 1, right, the probability of getting a false edge goes to 0. The reason is that as rho gets to 1, it will eventually surpass the largest sample correlation. So threshold, and therefore will threshold all sample correlations to 0, right? So the probability of detecting one false edge will go to 0. So both scenarios lead to degenerate or trivial limits. So what one needs to do is to let the threshold rho P tend to 1 at the correct rate as P goes to infinity to obtain a non-degenerate limit. And when one does that, it leads to very useful expressions for PE, which is the probability of obtaining a false edge. So we call it the purely high dimensional setting because only P goes to infinity, but N is fixed. So this is the motivation behind looking at this issue where we have this problem where, where we said, no, we can't really assume that N goes to infinity and both goes to infinity because modern settings don't always allow the setup. But we also want inference, not just model selection. So we need to quantify the behavior of these quantities, right? Of these sample correlations or sample partial correlations. With that said, we have a theorem, which I'm just going to briefly give intuition about, and then try and explain it in the ensuing slides. So consider NIID samples, which live on RP, which come from some bounded elliptically contoured density and blocks pass P by P covariance matrix. Right? So it doesn't have to be Gaussian, it can be much more general than Gaussian. Now let rho be the threshold applied to the sample or partial correlation matrix. Assume that as P goes to infinity, rho P goes to 1 according to a certain rate is given by. Right? So we're actually getting a rate so that we don't have a degenerate limit. Then the probability PE that there exists at least one false edge in the correlation or partial correlation network satisfy this, right? Where PE goes to this quantity, which is given by these expressions. So I won't go through that, except to say what we're able to do is, right, obtain theory that will control the probability of getting a false discovery. And you may have seen articles recently where there is this claim that 50 or 60% of articles in Nature and Science are not reproducible because many of them are, assume that there is a significant correlation when in fact there isn't, and a lot of it is due to the high dimensional nature of the problem at hand. So this is the main theorem that I wanted to briefly talk about. And the advantage is that it is true when n is fixed and p goes to infinity, number one, right? Number two, it's not iterative, so it's really scalable. It doesn't rely on optimization. And number three, perhaps more importantly, it gives us an inferential framework, a probabilistic framework. And I think therefore it's appropriate for this conference to try and control, right, a type 1 error. In this case, this happens to be the probability of obtaining at least one false edge, and we usually refer this to as fewer, or the family-wise error rate. So I'm just going to take a few slides and go through what we've tried to do was try and really tackle this setting as compared to the classical setting and the mixed asymptotic settings, which the lasso, which underpins the lasso. So the strengths of this theorem or this theory is that it certainly yields sparse solutions, right? Because the threshold can be used to remove noise or false discoveries or false correlations or partial correlations. It's non-iterative because we just can threshold the sample covariance matrix or some inverse of it, generalized inverse. So it's immediately scalable to ultra-high dimensional settings. And statistical or mathematical guarantees are in the regime when n is fixed and p goes to infinity. So in the purely high dimensional setting. So we have consistency in that. But what's more important, perhaps, is that it is amenable to statistical inference. We can do uncertainty quantification. It does not assume sub-Gaussianity. Heavier tails are allowed. And it also has some nice contributions and connections with other branches of mathematics. So the point I wanted to try and make is here is an alternative class of methods which really tries to overcome some of the apparent serious deficiencies of penalized methods. So what is the intuition or the theory or ingredients that underpins that? Well, the underpinning about the above results for that theorem fundamentally depends on quantities which we refer to as U-scores. So I'm going to talk about them in the next few slides. Intuitively, the U-scores are really a type of Z-scores. And we know what a Z-score is, right? When we take a random variable or random vector and we center it and normalize it. So it can be thought of as a centered and normalized versions of your original random variables. Now you have P of that because we have a P-variate problem. Your x's, right, x1, x2, up to xn, they live in Rp. So you have a P-variate a random vector. And when you have x1, x2, xp, right, for each of these samples, this is a sample, have a very high dimensional vector, and each of these features, can be centered and normalized, right? These U-scores are effectively a different but convenient ways to represent each feature or variable, and the properties of U-scores facilitate ultra-high dimensional statistical and mathematical analysis. I'm just going to talk about what these U-scores are. All they really are each feature that you have. And I'm just going to say x1, x2, up to xp for just the first feature, and I'm just say y1, y2, the yp, z1, z2, up to zp, and you can go on, right? Sorry, I meant to say zn, right? And you have a sample of size of n for feature variable 1, variable 2, and variable 3. So p is often very large, right? And n is small. So you have p features, and we take each of those features only and analyze them. We refer to them as U-scores. There is a little more needs to be done, but you can just think of them as a kind of z-scores. And the properties of these U-scores, right, facilitate a ultra-high dimensional statistical analysis. And recall that these U-scores are just normalized versions of each feature, right? So they really are n-dimensional vectors which lie on the unit sphere, right? Because if you have a sample of size n, so when you have a sample of size 4, right, and when you center them, you lose 1 degree of freedom. I'm looked at U-scores in the setting when sigma is equal to I in the null model, when the dimension is 500. What have we actually done? So if effectively we've transformed the data, our data, right, from a challenging high dimensional problems in p dimensions, right, which live in RP, into an easier problem of studying vectors which lie on the unit sphere, a space which is of a fixed and small dimension. Recall n is much fewer or smaller than p. So it's really neat. We've reinterpreted our data in a much lower dimensional space. That has many advantages, right? So you have each feature really that represents each of these dots. That's all we've really done. That's where they live. They don't live no longer in RP. But by doing this, by computing these R scores, it has some really useful properties which I'll go through, right? One of them is that the first property is that it lives on the unit sphere. That's the first thing. The second property is that you have these P features, and you can put them in a matrix, which is right U, denote the matrix of U scores, where Uj represents the youth score, or the youth feature, or the youth random variable. Now the correlation matrix R can be represented as U transpose U. So the U scores serve the same purpose as the original data and can be used to compute the sample correlation matrix R. Right? So that's the second property. The third property, which I think is really fundamental, is that the U scores are uniformly distributed on the unit sphere, Sn-1, when the underlying population covariance matrix sigma is diagonal. So when there are no relationships, the null model, they are distributed as uniform on the unit sphere. And this was a result that you can see in Anderson or Muirhead, right, in the books of those. And figure 3 provides an illustration of P, right, P features, P U scores living on the unit sphere in the case when the sample size is 4, when sigma is equal to I for the null model, right? So you can see that you can just see where these features are. And the proximity of the features to each other speaks to how highly correlated they are, right? And so the third property is that in the null case, right, if you want to do statistical inference and if you have a null hypothesis, right, in the null case, we understand the distribution of these high dimensional quantities. And this is a fundamentally important property, deriving the distribution, for example, of the maximal correlation in the setting when the sample size is fixed and p goes to infinity. Because if you recall, we looked at the distributions of the correlations and we wanted to understand what's the maximum one so that we can put an appropriate threshold to distinguish signal from noise, which is essentially a probabilistic question, right? More than a statistical question, but it's useful for statistical inference. So this fundamentally important property can be used for, right, the fact that the U scores are uniformly distributed on the unit sphere for deriving the distribution of the maximal correlation. With that said, the last property I want to say is that the sample correlation I and j between feature I and feature j can be computed as the Euclidean distance between U scores. So if you go to U score, the Euclidean distance between two U scores tells us it's directly related to the correlation coefficient. So your Rij is of course the inner product of Ui transpose Uj, can be written as 1 minus a half of Ui minus Uj, the L2 norm. So this is a convenient representation of sample correlations. So in that sense, right, the geometry of correlations is really embedded in this unit sphere. So that's really useful, a useful property. So I just want to quickly recap that these U scores live on the unit sphere, right? They represent correlations, and in the null case, these U scores are uniformly distributed, and the Euclidean distance between any U scores really is nothing other than the correlations. With that said, right, because the U scores are uniformly distributed on the unit sphere, which is property 3, And the spherical cap probability P0 that we saw here, this we call it the spherical cap probabilities, right? These probabilities, right? Like they precisely quantify the probability that a uniformly distributed point U on the sphere Sn-1 lies in a hyperspherical cone symmetric around the origin. So we're in a position to kind of work out how closely, right, how high a correlation is, because the magnitude of a correlation is really determined by how close the Euclidean distance between 2 points on this unit sphere, because of this, right, relationships. And because we understand the behavior of these points, how they're distributed in the null case, we're in a position to work out these spherical cap probabilities P0s. And property 4, right, which is of course the Euclidean, the fact that the Euclidean distance represents the correlations, it plays a pivotal role in characterizing the distribution of correlations which exceed a given threshold rho C. And so these results can be used to quantify the number of discoveries or correlations exceeding a given threshold rho C. So effectively, we are looking to see how many, right, correlations are close to any given feature, right? When the null model is that they should all really be distributed uniformly. How unusual is a very high correlation can be quantified because we can, very precisely understand the behavior of these U scores and therefore understand high dimensional probability, right? With that said, so we're in a position to say that so as P tends to infinity, the number of features, so the number of U scores, and your rho tends to 1, your threshold, the number of discoveries or correlations exceeding a threshold rho is approximated by a Poisson distribution with mean lambda as a function of P and N, where I'm not going to go through this except just to say we can quantify the number of discoveries, right, which are within some region around a feature on the unit sphere, right? So that's something that we can do, and we use, of course, methods from probability and Stein's method and so forth to quantify that. And the main theorem that I had put up earlier, right here, follows directly from this high dimensional Poisson result. And the result is valid when n is fixed and p goes to infinity. So those are the ingredients into that theorem or for that theorem. And I think the main takeaway message is that we can certainly fix n and let p go to infinity and deal with that particular asymptotic regime, right? So the theory that has been developed can be used to, for example, to control various multiple hypothesis testing metrics, modern ones, not the classical ones, such as we can control the family-wise error rates, fewer, or k-fewer. Fewer is often considered very conservative because just trying to make sure we don't even just get any one false discovery is very conservative, and we know that, right? Especially from using Bonferroni and other type of approaches. So we can generalize it to k-fewer, right? I.e. controlling the probability of obtaining k or more false or spurious correlations. And we are also in a position from the theory to get finite sample expressions for the marginal distributions of correlations. So we can also do FDR control. So we can actually quantify F fewer, K fewer, and FDR control. And the theory that we have can be extended to understanding the distribution of partial correlations in the setting when n is fixed and the dimension p goes to infinity. So overall, the framework that we have is an inferential framework, right, rather than an estimation one, which yields a highly scalable approach for undertaking graphical modeling for both undirected and bidirected graphs. So, standard concentration graph models or covariance graph models with uncertainty quantification, so inference in modern data regimes when n is fixed and the dimension p goes to infinity. Certainly, we benefited from the mathematical rigor that's required to getting those results, but we feel that that does, going back to some of the the strengths of the approach, the fact that it does yield statistical inference, and the regime, when it works, is much more modern. It doesn't require n to go to infinity. Is certainly useful for modern settings. So I'll stop there and see if you have questions, but perhaps I can use the last slide to talk about, in commemoration of Professor Lan Massam. She served as my postdoctoral mentor, a collaborator, and co-author, and was really the person who introduced me to the world of graphical models. I believe she has left a very important legacy in terms of research and scientific discoveries that are rooted in rigor, and she always emphasized that. The graphical models community is very grateful for her contributions at so many levels. She really instilled excellent values in her mentees and in her trainees, and I feel it's therefore, very I'm delighted that we are celebrating Professor Massam's lives and contributions here. I thank the organizers for giving me an opportunity to come and speak about our work, and certainly to thank Professor Massam for everything that she has done for so many people. So thank you, and I'm happy to take questions. Perhaps I should stop sharing, or yes, go ahead.
Questions, please.
Good morning, Bala. This is Piotr Gratic. I have a question about your theorem, the only theorem you showed, the limit of probabilities PE in the theorem was given by a formula which was not so easy to me to understand. So this limit, can it be small as we want when
yes, absolutely. Yes, you are absolutely right. It can be small as we want, because often in statistical applications, we want to control the probability of a false discovery, probability of getting at least one false edge to, let's say, 0.05, to some significance level, to 0.05. So yes, as small as you want it, yeah, of course.
So it means kappa n should be near 0. Yes, 1 minus e to the 0. We want limit PE be near 0 to have little false discoveries. And this expression, I don't understand it very well. Can we make it kappa n near 0?
Yes, so we can make the entire, there's also A of n, right? Yeah, A of n here. So yes, we can, for example, we've done that in applications where we've controlled it to 0.5.
N is fixed. And what is En in this formula? This can be little.
En is a quantity, I think that's because it's not actually mentioned here. So En is a quantity that's fixed in n that it's not here. It's a quantity that's fixed in n. Somehow
how to make kappa near 0?
What happens is that you can determine the value of rho p for a given p. The rho is what we will get, which will, there's rho that's still floating around, your correlation, your threshold rho. Mm-hmm. So you would use rho to do that.
Mm-hmm. So if rho p is very near 1, En is near 0. Okay, now I see it was too quick. So now I understand. Thank you.
No, thank you for the question, sir.
I point out that this is not 2b, but 2 over b.
I can't hear you, so I'm sorry.
Yeah, the people online cannot hear the questions from the audience in the room.
Well, this is just a small remark. Instead of 2b for an, you should have put 1 over 2b. The beta function is always smaller than 1.
Can you hear?
Yeah, not really, but yeah, maybe it was a small comment. Okay. It was.
They don't hear if you don't speak directly to the mic.
Okay, sorry. So an is a quotient of gamma function, but the expression of this quotient in terms of the beta second Euler function, it should be 1 over b.
Yeah. Okay, there's a typo then. Yeah.
Right.
So
Yeah.
That's right. And also the EN is defined here. I think Pietro, I thought I had not defined EN. Here is EN. Is that limit?
Yeah.
It's here where my mouse is. Sorry.
Yeah.
So it is defined. I mean, everything is defined. Yeah. I didn't leave it out. Yeah. So, but thank you for the question. Yeah.
No, Piotr Zwiernik.
Hey, Bala, it's Piotr. Just a quick clarification question. So in your setup, you had all the correlations equal to 0, and you were trying to make sure that none of them are identified as truly non-zero. So the threshold had to be set up high enough. But what with the setup that some of the true correlations are actually significantly non-zero, right? So in your ultra high dimensional setup, some of them in the sample, they can be relatively low. Is it crazy to expect that there's still some threshold that minimizes the type 1 and type 2 error at some point, or this is completely out of control at this point, which probably.
Well, I mean, the thing is, if you, no, I think it can be done, because that was the whole point, that because now you're starting to talk about, I think, moving from type 1 error, where we have the null model, to something such as, let's say, can we control also the type 2 error in terms of power? We've done some very recent work on it, and I didn't talk about it, but let me just say, I kind of allude to it even from this work, right? So we've done some work where we can kind of controlling power in this ultra high dimensional setting is already, just getting a limit law was tricky, but controlling power and looking at the alternative models is more tricky. But I also talk about finite sample expressions for the marginal distributions and FDR control. So that speaks to it. So we also want to make sure there is a balance between, your type 1 error and type 2 error. And if you can achieve that, and we're able to do that, because we have expressions for the marginal distribution of correlations, right? So at an individual parameter level, if you have a Neyman Pearson test, right? And we're able to really, when n is fixed and p is very large, we actually do have finite sample expressions and precise ones for the marginal distribution. So we can undertake FDR control. So you would really be, really also looking at power through that. And more recently, we've addressed that, but I didn't really talk about that more explicitly. Yeah, but FDR control, tries to certainly look at that. It's a very good question, because that's, can we go beyond, controlling type 1 error type quantities? And I think, one way to do that is through FDR, and this framework can achieve this. And what's really neat is that in the null model, the fact that these use scores are uniformly distributed allows us to really, work with a probability distribution that we can get a handle on. So, and that's very helpful. I mean, the fact that these use scores are uniformly distributed is available in Anderson's book. You do a polar coordinate transformation, and it's there, or in Muir's book, or whoever's. So, so I don't anyway claim that as our result. We have used it and analyzed it in the case when n is fixed and p goes to infinity to precisely get a handle the behavior of, for example, the number of false correlation beyond a threshold rho c. And that requires, of course, more advanced probabilistic techniques such as Stein's method and so forth.
Thank you. So more questions to Bala, please.
Yes, I have a comment and a question. So Bala, this is very interesting for me, because in the stock market, typically n is fixed and p is as large as you want it to be, right? P is essentially the number of characteristics that a financial analyst will use in analyzing a particular company or group of companies. And so it's not surprising to me, actually, that when n is fixed and p is extremely large, that the probability of obtaining at least one edge is going to be one false edge is going to be large. But this is the first time I've ever seen anybody quantify that the rate and even do any kind of probabilistic calculations on the probability of obtaining at least one false edge. So I actually think that right here you have, you know, I bet you could start a company providing financial advice on false edges, on the probabilities of obtaining false edges for the financial markets. Yeah, I really do. I mean, I really do think so.
You also, I mean, so, well, firstly, no, thank you for the kind and encouraging remarks. So one of the things we did do was to take this approach. I mean, the L1 or the GLASO L1 based methods, we did use them previously to do portfolio optimization, and they gave good results.
Mm-hmm.
And then we used this approach, and they gave even better results.
Mm-hmm.
And so we've looked at, you know, using it even for something which isn't very high dimensional, like the S&P 500. So, you know, Dow is very small. I'm not talking about 15 stocks, but even just 500 stocks. It was even better than these, you know, pseudo likelihood L1 based methods, which we've developed also. And so, yes, and I think people want to kind of understand, get an idea of the value at risk and get an idea of uncertainty, not just, you know, kind of like only just prediction, but they want an idea of risk. So this approach, I think, tries to get at that. So yes, there has been some interest actually from some. Good.
Make sure that your hourly rate is 2,000 an hour. Okay. Right. Now, I also had another comment, which is regarding the assumption of, I guess this is more of a question though, regarding the assumption of elliptical contouredness. Would it be possible to relax that? I mean, you know, ideally, it would be nice to be able to do it completely non-parametrically, and perhaps there is a kind of a high-dimensional version of Chebyshev's inequality that could allow you to put a probability on obtaining at least one false edge, but with no assumptions on the distribution of the underlying data.
So this is something that we've been working towards, and so initially just going out outside the Gaussian one. Of course, the fact that we leverage the fact that the U-scores are uniformly distributed, we've gone a little bit outside that, where we have settings where the U-scores are approximately uniformly distributed when there are no correlations. So we can go a little, we can push it a little bit, and we're trying to push it even further out, completely non-parametric.
Okay, good.
So
okay.
Yes.
All right, very nice. Okay, yeah, very nice talk.
We feel. Oh, thank you, Donald.
Thank you very much.
Thank you.
Oh, you're welcome. Yeah. Yep.
Thank you. Let's think.
Okay. Yeah. Great to see you. Yeah. All right. So we're